In this video, I'm going to talk about the Boltzmann distribution of molecular energies. If you consider any sample of a gas or a solution, you will find that the particles in that sample are not moving with the same velocity. They are all moving with different velocities. That is due to the random motion, because what happens is that the molecules or the particles, they keep on colliding randomly with each other, so that the velocities possessed by these different particles will be different and not the same. But how exactly are these velocities distributed among the molecules? For that explanation, I find this analogy to be very helpful. If we analyze the marks obtained by students at the end of an examination, this is the kind of distribution that you might expect. See, what's going to happen is that maybe about only 20% of the students score from 0 to 20% of the marks. And the percentage of students scoring 21 to 40% of marks may be about 15. But the majority of the students, say 50%, will be scoring marks which are neither too low nor too high. Let's say from 41 to 70% marks will be obtained by the majority of the students. And once again, the percentage of students scoring very high marks is also going to be a small percentage. So how does it relate to the distribution of the molecular energies in a sample of a gas or a solution? We didn't talk about the solids, because in the solids the particles are not able to move randomly. They just vibrate about their mean positions. So if you consider the sample of a gas or a solution, then just like this kind of distribution, you will get a similar distribution. And that similar distribution is going to be something in which something like this. That if you consider, see this on this axis, you have the molecular energy, right? So in this direction, the molecular energy is increasing. So this region represents the region of the molecular energies which are not too high and they are not too low. So most of the molecules, see the number of molecules is maximum in this range. So that most of the molecules which lie in this range, their energies are somewhere here. That is neither too high nor too low. So this is to be expected. This is what Boltzmann found out by his analysis, that most of the molecules in a sample will be having the molecular energies, which is due to the motion, the kinetic energy, which is not going to be too high and which is not going to be too low. There will be some molecules possessing very low energies in this region, and there will be molecules possessing very high energy in this region, and this is the highest amount of energy possessed by the molecules. Now, how does it help us in understanding the rate of the reaction? And that's what I'm going to explain you now. There is a term which is known as activation energy, which is being shown over here. This energy here is the activation energy, and activation energy is the minimum amount of energy which the molecules must possess in order that when they collide, then a reaction may take place. Why does that happen? That happens because if the two molecules collide with one another, because that is necessary according to the collision theory, and if they don't have sufficient energy, right? Suppose they have less energy than the activation energy. Then the molecules, they collide and they just bounce back. The bonds don't get broken, so there is no reaction. No reaction takes place because bonds don't get broken, because the energy is not sufficient to break the bond. For example, an HH bond. So in order to break this bond, there should be some minimum energy which should be able to break this bond. So unless this bond or other bonds in the molecules are broken, the reaction doesn't start. So the molecules must have minimum energy equal to the activation energy. Then only the bonds can break, and then only a reaction may take place. So if you observe this graph, then this shaded region is the number of molecules which possess the energy greater than activation energy. So only these number of molecules can lead to successful collisions and to success and so that a reaction may take place. Most of the molecules present here which have energy lower than activation energy are unable to take part in the chemical reaction. So this is how we can understand the distribution of molecular energies, and the number of molecules which are having energy greater than activation energy, those only succeed in bringing about a chemical reaction. Now let us see that what happens when we increase the temperature. So what happens when we increase the temperature? All right, so let's see that. So when we increase the temperature, we know that the rate of the reaction increases, right? Now let us see what happens what happens to the distribution of molecular energies as we increase the temperature. So this graph, so this is the graph which is at the temperature T degrees Celsius, and this is the graph which is at a higher temperature, which is 10 degrees higher than the previous temperature. So let us see what happens to the shape of the graph. What you observe is that the graph shifts towards the right. Now that means that now most of the molecules, so see, this represents the most of the molecules present here, right? Now the number of molecules, see, the number of molecules compared to the number of molecules in the previous graph, there is less number of molecules, but they have more amount of energy. See this energy which you find over here is higher than the energy which you found in the previous graph. That means the average energy, or now the more number of molecules have higher energy as compared to the number of molecules in the case when the temperature was lower. So overall there is a shift towards the right. That means overall shift towards more molecular energy, and now the maximum number of molecules possess energy which is higher on an average compared to the case when the temperature was lower. That's one thing that we observe, and the peak is obviously here lower. I'll tell you the reason. And then you see that the curve at t plus 10 is actually higher. See, this is higher than the curve which was there at the lower temperature. Now we know the activation energy remains the same. So the activation energy which was there for the lower temperature, the same activation energy, because activation energy depends upon the nature of the reaction. And the nature of the reaction or the reaction itself, we are not changing. So we are talking about the same activation energy. It has not changed, right? But the number of molecules which possess energy greater than the activation energy is the shaded region which you see here. And as you can see, this shaded region includes more number of molecules than the shaded region which was there when the temperature was lower. Only this number of molecules were having energy greater than activation energy at the lower temperature, but at the higher temperature there are more number of molecules which have crossed the energy barrier. Now where the number of molecules possessing energy greater than activation energy is much greater. Now one can also understand that why the peak has gone down, because this part of the graph is lying above the previous graph, but the total number of molecules is obviously unchanged. The total number of molecules at the higher temperature is the same. So total number of molecules remains the same. And therefore, the area under each curve, which represents the total number of molecules, is also going to remain the same. That means if you consider the area under the curve at t degrees, the area under that curve, and the area under the curve at the higher temperature, the total area under each curve is the same because the total number of molecules is the same. So obviously, if this part has gone above this graph, then this part must go below this peak, so that the total number of molecules remains the same. And moreover, now because of the higher temperature, there will be greater number of molecules which have the average energy has increased because the energy has been supplied in the form of heat by increasing the temperature. Now, one might say that the rate of the reaction increases when the temperature is increased because there are more frequent collisions, But is that the real reason? That is partly the reason. But the more important reason is that there is a greater number of molecules having energy greater than activation energy. So this fact should be very clear in the minds of the students, that the real reason for increase in the rate of the reaction on increasing the temperature is really due to a greater number of molecules which have energy greater than activation energy, and the other factor that there are more frequent collisions plays only a minor role in increasing the rate of the reaction. So I think you followed the Boltzmann distribution curve for molecular velocities and how we can explain the reason that the rate of the reaction increases on increasing the temperature, and what is activation energy, and how activation energy and the number of molecules possessing energy greater than activation energy actually determines the rate of the reaction. Thank you very much.